Let's do another warm-up. This one might take a little longer. See if you can get it done within about 10 minutes. Hey, here's a function f. I already gave you its derivative and second derivative. You should be able to find those if you need to on your own. But to speed things up, I gave those for you and I cleaned them up. See if you can sketch the graph without a calculator. Okay, hopefully you paused that video and gave it a try. I'm going to start collecting some information here. So, first thing I might want to find, order doesn't matter too much, but hey, I could look for my y-intercept. That's just when x is 0, so that'd be 0 root 0 plus 1. That's of course 0, so I get this nice y-intercept of 0, 0, right at the origin. Seems to happen a lot for us. I could look for all of my x-intercepts. I could of course have more than one of those. This is just going to be whenever y equals 0, or in other words, what is the root of that function? And that's going to be when either of the two factors is already factored for us, either of those factors equals 0. In other words, at x equals -1, and if I plug in -1 into this, I get a 0, or at x equals 0, and of course if I plug in I get a 0. That's not a coincidence that the y values are zeros. That's what we found, right? When x is -1, y should be 0. That's what an x-intercept is. Okay, on this problem, let's make sure that we take a moment to think about the domain. Because I have a square root, if I have a natural log or a root or even just a denominator, you should stop and think about the domain. And what I need for this to be in the domain is I need inside of that root to not be negative. In other words, I need x plus 1 to be greater or equal to 0 in order to be able to plug into that square root. If I solve this out, I just get x is greater or equal to -1. Okay, so I shouldn't have anything left of -1. If you don't stop and realize that you need to worry about that, you can do a bunch of work and maybe come up with a bunch of, say, critical points or inflection points that actually don't exist because they're not in your domain. Cool. Let's go ahead. I always like to finish off the work with f of x right away and say, what about my end behavior? In other words, what about those limits? Okay, I don't really need to worry about my end behavior as I go off to the left because my domain stops at -1. And in fact, I know what happens at -1, so I don't even need to worry about if there's like an asymptote on the left at -1, because at -1, I'm right on that x-axis. So let's think about what happens as I go to the right. This is not the world's hardest limit at infinity. Well, if I go to the right, x goes to infinity, and that square root also goes to infinity. So big positive number times a big positive number is just a big positive number. Great. So now I know my end behavior there as well. I'm going to go ahead and sometimes I wait for my critical point. In fact, let's go ahead. Let's find our first critical point here as well. Let's focus on this first derivative and find our critical values. So our critical numbers, that's just where my derivative is 0. So where's my derivative 0? Well, when the numerator is 0, assuming that that is also in my domain. Great. If I solve this out, it looks like I would bring the -2 over, and I would divide by 3. So x equals -2/3. And in particular, if I plug this back into my y value, I get -2/3, comma, oh, I got to plug that whole thing back in, so I'd get -2/3 times the square root of 1/3. I can clean that up a little bit. -2/3, comma, negative. How good are you with your roots? This would be negative. Square root of 1/3 is root 3/3. So this becomes 2 root 3/9. Okay, that's nice and exact. For the purposes of graphing, it might also be helpful for you if you do a decimal approximation. So -2/3 is about -0.67, and -2 square root of 3/9 is approximately, maybe put this into your calculator, so that y value is approximately -0.38. And that might help you graph it a little better sense for what that is. Okay, so I like to not go too far before I start putting some points on my graph. and writing down this behavior, because oftentimes a lot of the information ends up being redundant. So if I look at these points real quick, I've got 0, 0, I've got negative 1, 1, I have 0, 0, and I've got negative 0.67 and negative 0.38. So this tells me when I'm making this graph, I probably want my scale to be fairly zoomed in. Most of these numbers are in between negative 1 and 1. Because those numbers are small, I should, when I draw my axes, I should probably be fairly zoomed in. For instance, I gave myself a lot of room between 0 and 1 and negative 1 so that I can make a nice clean graph. Okay, putting in those intercepts, I had an intercept at 0, 0. I had an intercept at negative 1, 0. In fact, that's an end point. Maybe I'll go ahead and even blue that in right now, nice and big, because that is where my graph ends. And then I had a critical value at about negative 6.67 and negative 0.38. So that would be, right about, I don't know, there. Seems about right. And more than that, I also know my end behavior, that in the long run, this thing should be going up to infinity. And it shouldn't cross the x-axis anywhere else. It shouldn't really be doing anything. It shouldn't be changing its up and down direction. I've got a pretty good idea of what's going on. Maybe I should check for concavity before trying to sketch this in and say, okay, where is my second derivative 0? So if I'm looking for inflection points, that's where my concavity might change. And the first thing I'd want to do is say, where is my second derivative 0? If I solve that, I get, looks like negative 4 over 3 equals x. And I might be tempted to plot that, but by the way, this is not in my domain. That is less than negative 1, so actually I don't have any inflection points. Here's where getting that domain right away helps you out a lot. If I know that the curvature is not changing, and I know that the only time I can switch from going down to going up is at this beautiful critical point right here, well then my graph pretty much has to look something like that, right? The concavity can't turn, I can't change directions up or down other than at this point right here. That's pretty much what this thing has to look like. And I saved myself a lot of work in the end. I'm going to go ahead and check some of this other information, but that's it. From your points, you can usually tell a lot about the shape without going into lots of first and second derivative tests. Okay, with that said, let's go ahead and see if we can figure out where we're increasing and decreasing, maybe just to check our work. So to do this, I'm going to want to basically plot out f prime. I'm going to want to plug in all of my critical numbers here. So this ends at negative 1. It doesn't exist, but that's the end of my domain. If I plug in negative 1, I would be dividing by 0. That'd be bad. And I also have a critical point at, say, negative 2/3. And that's where this is 0. And if I plug in a number like 0 into my derivative, then what I find is I would get 2 over 2. I get a positive number, which means that my derivative should be positive when I'm bigger than negative 2/3. And if I plug in a number in between, like say negative 3/4, well, I get something a little bit nastier, but I get a negative. Okay. Overall, what that's telling me is that the shape of my graph is it's going down and it's going up, and the place that it changes is at negative 2/3. Is that what happens here? Looks like it's going down and then it's going up, and the place that changes is at that negative 2/3. That is perfect. I don't have any change in concavity. There's no inflection points. But I could go ahead and check my concavity if I really want to. Negative 1, this thing doesn't exist. And then just goes off to infinity, right? There's no other places where it might change. So if I just plug in a number like, say, 0, I would get 4 over 4, which is a 1, and so I get plus. This thing should be basically curving up the whole time, and lo and behold, it is. Looks like we've got a pretty good graph. The amount of information you have and what you need is going to change a little bit from function to function and graph to graph, right? Sometimes you have to deal with vertical asymptotes. Sometimes you don't need to worry about these domain issues. But almost always, some of the information ends up being redundant. And that is good to know, because maybe you don't need to do as much work, but also it can quickly let you know that something has gone wrong. If we said that the concavity was going down, but somehow I had to hit these 3 points, well, there's no way to hit these 3 points with a downward concavity. Okay, so you can also use it as a check on yourself. All right, hopefully this is getting easier the more we do it. Keep practicing, and the only way to practice these is really just to give yourself a little time to work on one.